Okay, so now that we learn about the correlation coefficient, how the strength and the direction of the data and how that relates, now we're going to test for a linear relationship. So if, let's say we don't have a graph of and see what it looks like, right? We just have a correlation coefficient. So we can look at this critical values for the correlation coefficient chart. So first thing, we want to get the absolute value of the correlation coefficient. So just make it positive, whether it's positive or negative, right? I'm not concerned if it's going a positive slope or a negative slope. I just want to know how tight the data is. Find, oh my, look at that, critical value in table 2 from Appendix A in the given sample. This is going to be a link in the homework, so you'll have that. It's in your notes too, which is nice, but it'll be a link in the homework. If the absolute value is greater than the critical value, there is a linear relation. Otherwise, no. So it's just the correlation coefficient has to be greater than the critical value. And you get the critical value from this chart. And we need to use our variables that we know in order to determine that. So let's pull this. So using the results from example 3, so I know my R here is 0.939. It's already positive, so I don't have to worry about that. But the other piece of information here, let me swing it back over, is we have our R is 939. I'm going to make this bigger so we can see it. Look at this. We have 1, 2, 3, 4, 5, 6, 7, 8 pieces of data. All right. So that tells me that N equals 8 here. So if N equals 8 that we have, N is the sample size. So we have our 8 right here. This is the critical value. And these are just columns, right? So there's this column. Once you get to 9, then you come up here to 10 with this column. It's just how they have it laid out, all the way up to 30 pieces of data. Starting with 3 pieces of data up to 30. And we want to focus on the 8 for this particular problem. So that tells me I'm going to take the absolute of 0.939. I want to know if that is greater than 0.707 because that's my critical value. Is 0.939 greater than 0.707? Yes. So because this is true, therefore, there is a positive linear relation. And I know that this is positive because my correlation is positive. That's what makes that positive. And it is a linear relation because of this relationship tells me that it's a linear relation. Now, I just realized I put these 3 little dots up here. You may not know what that means. 3 little dots in a row just means therefore. I'll take those off. You can put them on there and take it off. That's just the math nerd in me coming up with with the math symbols. Those 3 dots in a triangle just means the word therefore. It's like stating the sentence, bringing it up. I don't expect you to write that, and that's not on anything else in statistics, so I'll take that off of there. But that's what that was, in case you were like, wait, what are those dots? Just a math symbol, meaning therefore. It's what you do in a proof whenever you state your conclusion. So I was stating my conclusion is what happened there. All right, but for our intents and purposes, it's positive because the relation is positive, or it's a positive relation because the correlation coefficient is positive, and it's a linear relation because my critical value is less than my correlation coefficient. That's it, right? Those 2 little things is all that it takes to make that proof. All right, we've heard of a lurking variable before, so let's talk about it a little bit more here. So a lurking variable is related to both. That's the key when you have this, the explanatory and response variable. Because I have 2 variables that relate to my piece of data, then my lurking variable has to also relate to both of them in order to be able to pull that off. Okay, that's a thing. All right, so here's an example, and we're just going to kind of talk through this example a little bit just so that you can see what this looks like. All right, because colas tend to replace healthier beverages, and colas contain caffeine and phosphoric acid. Researchers Catherine Tucker and Associates wanted to know whether cola consumption is associated with lower bone mineral density in women. So table 4 over here, boom, lists a typical number of cans of cola consumed a week and the femoral neck bone mineral density for a sample of 15 women. All right. The data were collected through a prospective cohort study, which we now know what that is, right? Putting them together and working it through. Figure 9 shows the scatter diagram, boom, of the data. The correlation between the number of colas and the bone mineral density is negative 0.806. The critical value with n equals 15, because there's 15 pieces of data, is 0.514. Because the absolute value is greater than the critical value, we know that this is a linear relation, and because my correlation was negative, it's a negative linear relation, right? What we just talked about. So this exists between the number of colas consumed and bone mineral density. Can the authors conclude that an increase in the number of colas consumed causes a decrease in bone mineral density? Identify some lurking variables. So this is where you have to set it up. This is where, how do I want to say this? This is where in statistics you have to be a good consumer and look at the words that are used. Causes this. Based on 15 pieces of data, you're going to say this is a cause of what can happen, right? Your correlation coefficient is fairly strong, right? It's fairly strong that we're looking back through there. However, is it a cause? What are some things that could be lurking variables? Just throw out some stuff. Genetics, right? Maybe you have poor bone density in your family. It doesn't matter how many sodas you're going to drink. Boom, it's going to happen. What about physical activity? Physical activity. That makes a difference in bone density, right? Other aspects of your diet, not just the cola. Right? There are tons of variables that can happen here that can affect both the quantity of cola and the number of cans of cola and the bone mineral density, right? So it's affecting some of those aspects of it. Your age. It doesn't give an age in there. It just says 15 women. So are they older? Are they younger? I don't know. It doesn't say. So those are things that we have to be looking at. And do you see how we can just keep going and keep going and keep going? So then that makes an impact. Okay, so in this actual study, like whenever they did this, they said, based on, so look at, I'm going to scoot this up here. Based on data obtained from Catherine L. Tucker, colas, but not other carbonated beverages, are associated with low bone mineral density in older women. They don't specify what that is. The Framingham Osteoporosis Study. So that's where it comes from here. But I want to point out that word associated. Because do they use the word cause in their topic? No. Right? Right. So there is an association, but they're not saying that it is the cause. So I want to point that out. The authors were careful to say cola consumption is associated, not the cause. The authors were careful to state cola consumption was associated, not the cause. Because that could really be an issue for them, right? So I just want to point that out to you as you're going through here and just pay attention. There are lots of lurking variables. You can't account for all of those. That's what makes an impact on it. All right. Man, this is getting good, right? Stay tuned. More to come.